Hello, Sauce here. This is an AP Calculus video lesson. I'm going to review two concepts, composite functions and inverse. We're going to review them together, so it's going to be fast. I'm going to write a couple of functions to work with. I'm going to define the L function that takes x as an input, triples it, and then adds 2. This is function notation. This is the expression 3x plus 2 for the function L. I'm going to define another function, we'll call it M, and it takes the input, subtracts 2, and then we'll divide everything by 3. We have an L and an M function defined. So what do we mean by composite function? We mean a function composed with another function, rather than simply the function L taking an input x, which is a number. We can write the notation for L composed with the entire function M, and M is going to receive x as input. This is composite function notation. But what math is done if we wanted to know what the expression for the L of M of x function is? Well, we would have to take our functions here and create the expression for it. Let's keep it organized. The way that I prefer to make composite functions is to think of the outside function first. It's L that's going to be composed with M, so we have to fit M into L. The way I organize that on a page is I'm in the practice of using parentheses, wide empty parentheses, to represent where the input of the L function is going to go. And what do I do to the input? Well, in the expression for L, x represents the input. Now I have not x, but very wide parentheses. And what I'm going to do to the input is I'm going to multiply it by 3, and then later add 2. I've prepared the L function so that I can put M into it. And the M function is x minus 2 all divided by 3. So inside the parentheses where I put the input, I'm going to write the expression for M. I'm putting parentheses around the x minus 2 because I want to make sure that I divide all of that by 3. This is the expression for L composed with M. And it looks like I can simplify it a bit. So I'm going to go ahead and distribute the 3. When I multiply this 3 by this fraction divided by 3, the multiplication and the division will cancel out, leaving x minus 2, the numerator, and then outside the parentheses, plus 2 is still hanging out. I can simplify this further. If I drop the parentheses and subtract 2 and add 2, they cancel out, leaving x. This isn't a surprising result that the composite function's expression reduced to just x. That doesn't often happen, but when it does, it indicates that L and M are inverses of each other. What happened when I composed L with M is that L's expression canceled out M's expression, leaving simply the variable x. L and M are inverses of each other. And anytime you have a function composed with its inverse, and they cancel out, leaving just x, then this is evidence that they're inverses. And when they're inverses, we can also form the other composition, M composed with L, and they will cancel out the same way. So L and M are inverses. Another way to see this is to take one of the functions, as we will now. Let's use the M function. And go through the process of finding the inverse of this function M. And if L is the inverse of M, the result will be when we find the inverse of M, it should turn into the L function to show that they're both inverses of each other. Let's go through the process of finding the inverse of M. I've written the expression. The first step is to replace the function notation with y, traditional variable in algebra. And when we replace the function notation and we have x and y, we can now take the inverse of this function, this expression here, by replacing every y with x and every x with y. In other words, we switched x and y. If I solve for my new y, it's going to create a new expression. Let me do that by multiplying both sides by 3 first. And then adding 2 to both sides, we'll get y by itself. I'm going to put y on the left side. And after I have added 2 to both sides, I get the expression 3x plus 2, which is different than what I started because the result here is the inverse of what I started. I could replace the function notation. If I started with the function that I called m, then I could choose to name this inverse with the same letter but include the notation for an inverse, which is a superscripted -1 by the function's name. So this is the inverse of m, or m to the -1 of x. And this is the same expression that we previously defined as L. Another way to show that the m and the L function are inverses. Graphically, let me remind you that if we have a function graphed, in this case, I tried to be precise. This point right here is at coordinates 0, 1. The graph of this function looks exponential. Let's imagine that it is the graph of the function 2 to the x. And we can find an inverse of a graph by reflecting over the line y equals x. This perfectly oblique line that has an equation y equals x. If I reflect over that, then I produce a graph, the inverse of a graph. This function here has been reflected across this line. The point of intersection now has coordinates whose x and y values have been switched. If the graph is an inverse, and an inverse means switching x and y, then that happens to every coordinate as well. We can highlight that it's happened to this coordinate. And the inverse of the 2 to the x function is log base 2 of x. Graphic inverses are reflections of each other over the line y equals x. A little bit more about composition. Let me show you an example of how to make a composition that includes 3 functions. I'm going to define another function up here. Let's call it the b function. And the expression for it will contain the variable twice. So let's provide an example. Let's form the composition b composed with L composed with m of x. How do we do that? It's a feat of organization. What I like to do is I like to take the outside function, and because I'm going to put a composition into the b function, then I'm going to make the space for my input very large. I'm going to make large parentheses, and I need to square the input and add the input again, so I'm going to use large parentheses a second time. This here is the structure of the b function, but instead of x, large spaces to put the new input. And what is the input of the b function? It's L composed with m. So inside these parentheses, I'm going to write the structure of the L function, which is 3 times input, large parentheses again, plus 2. And the input in this parentheses is going to be the same structure, 3 times some input plus 2. So this is the structure of the L function, and the parentheses represents the input. What are we going to put into L? Look to the notation, we're putting the entire M function. So inside these parentheses, I place the M function. X minus 2 all divided by 3. And then a second time, x minus 2 all divided by 3. Now, this here looks like it could be simplified. But unlike before, I think this time that if we simplified it, it wouldn't reduce to just x. We would clean it up and make an expression for it. And it would probably not be just x, because the B composed with L composed with M is not intended to be the inverse of anything that we started with. But I'm not going to simplify it. This was an example of how to compose a function with 3 functions together.